Hello, today I will be talking about polymers in transport. High-performance polymers are polymers that reach higher requirements than typical engineering plastics. The continuous surface temperature of a polymer defines whether it is a high-performance polymer, and those polymers whose continuous surface temperature exceeds 150 degrees Celsius fall into this category. Currently in the car industry, more of these polymers are being used than steel by volume. Their lightness helps cut fuel consumption dramatically, and in a car weighing 1 ton, using just 105 kilograms of high-performance polymers instead of metals makes a fuel saving of up to 7.5% possible. Other properties of these polymers, such as their durability, resistance to corrosion, flexibility, and needing little maintenance, finds them used in other industries such as rail, aerospace, and marine. Specifically in the aerospace industry, they can reach the aerodynamic requirements necessary to be used in military jet and helicopter panels, helicopter rotor blades, and much more. Their ruggedness makes them ideal for use in engine and carriage panels and trains, as well as in flooring, seating, and doors. In addition to greater temperature stability, high-performance polymers have greater chemical resistance and mechanical properties compared to engineering plastics. Currently in Britain, the transport industry is the second highest consumer of these polymers, with a 24% market share, and polymers such as PEK, PAI, PEEK, PPSU, PPS, PSU, and PES are frequently bought. The significant difference between the application of engineering plastics and high-performance polymers is that the latter are typically exploited for one sole purpose, such as their heat stability. On the contrary, engineering plastics yield greater use by providing moderate performances over a wide range of properties. In addition, the cost between the two is also significant. High-performance polymers tend to cost around $15 per kilogram, which is astonishingly between 3 to 20 times more expensive than engineering plastics. Having mentioned the properties that define a high-performance polymer, I will now touch upon why they have such stable thermal properties and consequently good mechanical properties that can withstand extreme temperatures. It is common for high-performance polymers to incorporate aromatic units into the polymer chain that, when linked with the elements oxygen, sulfur, or nitrogen, increases the polymer's continuous surface temperature above 200 degrees Celsius. Rigid side chains are also typically seen in these polymers, resulting in decreased flexibility of the polymer chain and more energy needed to overcome the barrier to chain movement. These features of high-performance polymers make them less likely to undergo thermal degradation until higher temperatures. On the right of the slide, you can see the polyphenylene structure that consists exclusively of aromatics and is stable at temperatures greater than 500 degrees Celsius. Fluoropolymers also boast a high temperature resistance of 260 degrees Celsius, but the poor mechanical properties of these polymers render them of no use in transport applications. Thermal degradation is the process where damaging chemical changes to the polymer take place at higher temperatures or when exposed to UV radiation. One type of thermal degradation is statistical chain scission, proceeding via a radical mechanism. During this process, radicals are formed on the polymer backbone either by hydrogen abstraction or side group elimination that can cause the polymer backbone to fragment. The formed radicals from this process are highly reactive and undergo disproportionation termination reactions. Aromatic units can offer protection against this because they can delocalize the free radical through the pi system of electrons, decreasing reactivity. At the bottom of the slide is a typical example of an aliphatic polymer chain undergoing statistical chain scission. The second type of thermal degradation mechanism is depolymerization. This process occurs when polymers are exposed to temperatures above their sealing temperature and the depolymerization rate is greater than that of polymerization. This event effectively inhibits the formation of polymer, as monomer units are lost greater than monomer units forming polymer chains. Polymerization, unlike statistical chain scission, occurs slowly, as the polymer chain only loses monomer from the end of the chain one by one. Below is an equation representing the hydrolysis of cellulose to glucose, a depolymerization reaction, illustrating how chemicals and fuel can be generated from biomass. It is often the case that high-performance polymers need strengthening to be of any use in demanding transport applications. Fiber-reinforced polymer composites, or FRPCs, are materials made from a polymer matrix and a fiber reinforcement. The fibers and matrix differ either in form or macroscopical composition, hence these materials are referred to as composites. There are several different arrangements of fibers within the polymer, including 1D, where the fibers are all arranged in the x direction, 2D random, where the fibers are randomly arranged in both the x and y direction, 2D orientated, where the fibers are aligned in x and y direction in a particular pattern, and finally 3D, a random arrangement of fibers. The polymer matrix and fibers have different roles in improving performance of the material. The polymer matrix protects the fibers from environmental and mechanical damage by transferring stress through these reinforcing fibers. The fibers themselves provide additional strength and rigidity to the high-performance polymers. Commonly, these fibers are either glass, carbon, or aramid. Different fibers induce different properties into the polymer. Aramid fibers provide the FRPC with good chemical resistance. Glass fibers are unaffected by UV rays, whilst carbon fibers provide the FRPC with both properties. The resultant formed composites often have greater strength and stiffness to weight ratios as well as corrosion resistance than many metals. In fiber-reinforced polymers composites, there exist two main branches of fibers used. The most commonly used fibers are synthetic fibers, including the likes of carbon mentioned on the previous slide. These composites are mechanically robust, but fall in terms of biodegradability, price, and recyclability. A second exciting branch is natural plant fiber reinforced polymer composites, or NFRPCs. These composites are highly biodegradable, cheap, light, and highly accessible due to access of renewable resources. Unfortunately, these polymers currently cannot replace synthetic fiber reinforced polymer composites in multiple applications as they do not have the same mechanical strength. Over the following two slides, I will cover the two main types of high-performance polymers used in fiber-reinforced polymer composites, the first of which is thermoplastics. Thermoplastics are heated up and molded into a desired shape with subsequent cooling to harden the object. Through repeating this process, it is effortless to recycle thermoplastics. Thermoplastics can be further divided into two subcategories, amorphous thermoplastics and semi-crystalline thermoplastics. The former thermoplastics have random chain structures and behave rigidly below their glass transition temperatures, or TG, yet rubbery past this point. The glass transition temperature of a polymer refers to the temperature at which individual chains in a polymer have enough energy and can move past each other in the solid, making the polymer soft and flexible. It usually indicates how useful a polymer will be in transport, as polymers with high TGs will remain strong and rigid whilst exposed to high temperatures. Amorphous thermoplastics also have good dimensional stability and are unlikely to warp during the warping process. They also have good stiffness and impact strength, but begin to soften when exposed to heat. Their appearance is consistently transparent. The second type of thermoplastic used in fiber-reinforced polymer composites is semi-crystalline thermoplastics. Contrarily to amorphous thermoplastics, these polymers have an ordered chain structure and do not soften when exposed to heat, as they can behave strongly past their glass transition temperatures, as the crystalline regions remain ordered and provide structure to the material. Strong molecular bonds in these thermoplastics make them resistant to chemical attack. Fluoropolymers are semi-crystalline thermoplastics, and PTFE, or Teflon, is a fluoropolymer that is used in cookware and electrical appliances due to this property. Semi-crystalline thermoplastics notably have an opaque appearance. Thermoset polymers are the second type of high-performance polymer used in fiber-reinforced polymer composites. These polymers are rarely used in transport as they become charred upon heating and therefore cannot be reshaped and recycled. The structure of thermosetting polymers differs to thermoplastics drastically. Thermoset polymers have crosslinks that tie polymer chains together, effectively creating one giant molecule. These crosslinks provide a robust chain structure that means these polymers can be used well past their glass transition temperatures. Properties such as good chemical resistance, dimensional stability, and heat resistance are attributed to thermoset polymers. Interestingly, they do not have a melting point. Polyetherimide, commonly called PEI, is a high-performance polymer, specifically an amorphous transparent thermoplastic. It is heat and solvent resistant and has outstanding mechanical and electrical properties, high tensile strength, and low smoke emission. Due to long-term creep resistance, it is routinely used to replace metal in structural applications. PEI is produced by a step-growth polymerization, specifically condensation polymerization, the synthesis of which is drawn out on the next slide. Here is a three-step mechanism process of PEI synthesis. The future of polymers in transport is both a positive and concerning topic. The first slide highlights their growing use, and the next slide presents some doubts accompanying this research. Today, ever increasingly, high-performance polymers and their composites are finding use in transportation industries, most notably the aerospace industry due to a recently renewed focus on space travel in the previous decade. Traditionally used metals in aerospace, such as aluminium, are being replaced by lighter, stronger, and more durable polymers. In 2018, the initiative to further progress in the polymer field was emphasized by NASA, which invested $15 million for the research and generation of composites for manned missions to space, hoping to replace currently popular FRPCs such as polyether-keto-keto, abbreviated to PEKK. Whilst the progress of research into high-performance polymers is promising, there are still many doubts of their increasing usage in transport. The high costs of high-performance polymers are unlikely to decrease in the future, since the investment costs for production equipment, the time-consuming development, and the high distribution costs will remain constant. Aircraft panels made of fiber-reinforced polymer composites cost significantly more than manufacturing aluminium panels, and so the use of these polymer composites in more competitive transportation fields such as the car industry is harder to justify. It also should not be underestimated the time and experience engineers have in working with traditional metals. The polymer field is not yet developed enough to encourage many engineers to drop their faith and confidence in materials such as aluminium in aerospace. It is also unclear how many high-performance polymers behave over various conditions. Long-term aging needs to be explored before further implementation into transport services. It is already widely known that polymers can be subject to accelerated aging due to exposure to moisture, ultraviolet radiation, and elevated temperatures, which have undetermined effects on the mechanical integrity of composite polymers.